All right, today we're popping the hood on a really simple but powerful money-saving trick in AI called prompt caching. Seriously, think of it like the ultimate tune-up for your language models, one that can just slash your costs and seriously boost your speed.
So let's just start with a really basic question. Imagine you've got this brilliant AI assistant, right? And you give it a 50-page manual to do its job. Now imagine every single time you ask it a simple one-sentence question, you have to hand over that entire 50-page manual again. Sounds crazy and efficient, doesn't it? Well, guess what? That is exactly what is happening in countless AI applications right now. And this schematic right here just lays it all out, the problem and the solution. On the left, you've got your standard stateless call. That's like building an entire car engine from scratch every single time you want to turn the key. But on the right, you have the cached call. The engine is already built, it's warmed up, it's ready to go. All you have to do is hit the gas.
So here's the game plan for this explainer. First, we're going to diagnose that core problem, the stateless API. Then we'll look under the hood at the engine's built-in memory, the KV cache. After that, we get to the real secret sauce, the prompt cache revolution. Then, of course, we'll talk about the bottom line, the incredible ROI, and finally, we'll peek at some even more advanced ways to tune this thing up.
Okay, let's jump right into our first section. To really get why this solution is so game-changing, we have to get our hands dirty with the problem itself. And that all starts with the way most APIs are designed right out of the box.
So here's the official definition. Stateless basically just means the server has total amnesia. Every single request you send is treated like it's the first time it's ever heard from you. It has zero memory of what came before. And while that's great for some simple things on the web, for AI, where context is literally everything, it creates a massive, massive bottleneck.
And this forgetfulness, it has a very real price. You literally end up paying for the exact same text, your giant system prompt, your context documents, to be processed over and over and over again. That's just wasted compute. It means a slower app for your users, and it means a much, much bigger bill at the end of the month. So how do the models themselves try to fight this inefficiency? Well, the first layer of defense, the first bit of optimization, is this really clever mechanism that's built right into the transformer architecture. It's called the key value cache, or just KV cache for short.
The KV cache is basically our first big efficiency upgrade. See, instead of recalculating the relationships between all the words in your prompt, every single time it generates a new word, the model stores these calculations, these key and value tensors, in its short-term memory, right on the GPU's VRAM. It keeps the engine warm, but here's the catch. It only does it for a single, continuous request.
So let's just walk through this blueprint real quick. You send a prompt, and the model computes the key and value vectors for each token, and it stores them in the cache. Then, to generate the next word, it only has to compute a new query vector and check it against all the keys and values it's already saved. This little trick avoids a ton of redundant work, but only within that one generation.
And this isn't some tiny improvement we're talking about. I mean, for a single long output, the KV cache by itself can make things over 4 times faster. That's a huge deal. But, and this is a really big but, it gets completely wiped clean after every single API call.
And that brings us to the revolution. The KV cache only helps inside one conversation. But what if the first 10,000 tokens of your prompt are exactly the same across thousands of different user requests? This is where we find the mechanic's real game-changing secret. I mean, this quote from the research paper just lays it all out. The big idea is that we can take those key and value attention states, the stuff the model calculates, and we can store them long-term. We can pre-calculate the state for our giant system prompt just one time, and then reuse it for every single call that comes after.
So what exactly are we caching here? Well, basically anything that's static and gets used a lot. The most obvious thing is your main system message, right? But this also works for huge documents, code libraries, even just standard prompt templates you use all the time. The researchers call these things prompt modules, which is the perfect name. It's like having pre-built engine components just sitting on the shelf, ready to go.
Okay, so let's get to the good part. What's the actual return on investment here? Why is this such a massive deal? Well, to put it bluntly, the results they're almost unbelievable. It's like finding this giant engineering loophole that basically just prints free money.
And here is the core of the magic. With prompt caching, the model just stops processing the entire input. So if you've cached that 50-page manual and your user asks a simple one-sentence question, the model only processes that one new sentence. All that context, it's just loaded instantly from memory.
I mean, just look at this example from the Llama Index docs. The API call only had to actually process 9 new tokens from the user. Meanwhile, more than 17,000 tokens of context were pulled instantly from the cache. That is where the magic happens. You're simply not paying to reread those 17,000 tokens every single time.
And this translates into just mind-blowing speed, especially for time to first token, which is how long you have to wait for the AI to even start talking. We're talking about an 8x speed up on a GPU. But look at the CPU numbers, a 60x speed up. That's not a typo. This suddenly makes powerful AI on cheaper, more accessible hardware a total reality.
So when you stop paying to reprocess tens of thousands of tokens on every single call, the cost savings are just astronomical. For any application that has a big, static chunk of context, seeing a 90+% reduction in your API bill is not an exaggeration, it's real. This fundamentally changes the economics of building with AI.
But wait, there's more. For those of you who want to tune the engine even further, the story doesn't just stop with caching identical text. We can build systems that are even smarter than this.
And that brings us to something called semantic caching. So instead of looking for a user's question that's an exact text match, this uses vector embeddings to see if a conceptually similar question has been asked before. And look at the difference. This can take your cache hit rate from maybe 30% all the way up to 87%. It's just another layer of incredible efficiency.
Which leaves us with this one final provocative question. Caching isn't some new exotic tech, right? It's a foundational concept in computer science. But applying it here can literally make or break the business model of an AI product. So now that you know the mechanic's secret, it completely changes how you look at the engine of AI. And it kind of makes you wonder why everyone isn't already doing this tune-up.